So in part 1 of chapter 4, we covered what types of graphs we would use for quantitative data. In the second part, we're going to actually look at how we want to analyze each one of those different graphical displays to mine important information. So the things that we look for when we're looking at a quantitative distribution is we like to always describe the shape, center, spread, and any unusual values. We often call those outliers. And if we are trying to remember this, when we are doing an analysis of any quantitative data, you always have to remember your SOCs: shape, outliers, center, and spread. So let's look at each one of those pieces, and then we will save some examples for the third part of the video for chapter 4, and then we are done. So when we're looking at shape, center, and spread, this is what we use in describing a distribution. And these are the things that you must describe. So if we look at these two different distributions, there are two parts of any distribution that we want to analyze. The stuff in the middle, we call the body, and the stuff on the end, we call the tails. There are always two tails in a distribution. This gives us what the shape is. So to go a little more specific on shape, we are looking for humps, which we call modes. We're looking for the symmetry of the distribution, and we're looking for any unusual features or outliers. So you should ask these questions. Does the histogram have a single hump or several humps in the body? Is the histogram symmetric? Does the body tend to the center of the distribution of values, or is it to one side or the other? We call that skewed. Are the tails similar in size, or does one tail extend out longer than the other? If you have something like that, that would be unusual. Do any unusual features stick out? Are there gaps in the data? Are any data values off by themselves? Those could be outliers, whether that's in the body or in the tail. So these are the things we're looking at. To be a little more specific, if we're talking about humps, does the histogram of the distribution have a single central hump, or does it have multiple separated humps? Now I say humps, another way of saying that mathematically is modes. And if you remember, modes means most value. So it would make sense if you have a histogram that the mode would be the largest of the bins. This is a somewhat different definition of mode than one you have learned in elementary class. So a distribution with only one main hump or peak in the graph is defined as unimodal. So one hump, unimodal. Two humps, we call that bimodal. A histogram, usually with three or more humps, we would say is multimodal. And what do we mean by this? So in these bimodal histograms, we can see that there are two distinct peaks. In this one on the left, we can see the first peak is somewhere between 70 and 90, and then the second peak is between 120 or so. And you might be thinking, what would give this distribution? If I told you this was a measure of blood pressure, your systolic and diastolic blood pressure, generally a good blood pressure is 120 over 80. Or in a different way of having a distribution, we could look at galaxy color and then the frequency in terms of the percent that those show. Both of these would be bimodal distributions. A distribution that doesn't appear to have any significant peaks or modes, or if they're approximately the same height, we call those uniform distributions. Now, note this word approximately. They don't have to be the same height, but if there's no distinct mode or hump, then we are going to say that they are uniform. Next up, with symmetry. Symmetry, we've talked about in previous math classes, is like a fold. So if you can fold the histogram along a vertical line through the middle and have halves match pretty closely, we say the histogram is relatively symmetric. It's never going to be exact because statistics is squishy, but we're looking for approximate. So if your graph is not symmetric, so usually the thinner ends of a distribution are called the tails. If the tail on one side stretches out further than the tail of the other, the histogram is said to be skewed. And we always indicate the skewness to where the tail is. So it's a little different than you might think, but in this distribution, the tail is on the left side. So we say it's left skewed or negatively skewed. In this secondary distribution, we have right skewed data because the tail is on the right side. We could also call it positively skewed. Generally, we use the directional terms. So take a look at this picture of a whale. Miss J is the one that gave me this, so you can thank her if you want to. But if you want to remember which way something is skewed, just draw the picture and see where is the whale's tail. If the whale's tail is on the left, it is left skewed. If the tail is on the right, then it's right skewed. To move on to things that are unusual. Unusual for displays of data, we look at gaps. We also look at outliers. So do any unusual features stick out? So sometimes it would indicate something of interest or importance. Gaps mean something when we are measuring continuous information. I will make a word of note. You must always mention any loners, always. Loners or outliers that stand off away from the body of distribution, and we need to explain those away because they will have potentially drastic impact on our analysis. Likewise, are there any gaps in the distribution? Always acknowledge gaps in the data. Gaps suggest potential multiple groupings. So we have outliers that are unusual, and we have gaps. So for instance, take a look at the following negatively skewed or left skewed histogram that has a gap in the data and some potential outliers. Now, if we looked at this data, we don't see any labels on our X or Y axis, nor are we missing a title. So all of those would give us more context to what this data is displaying. We do see there is a peak in the data from about 37.5 to 47.5. That's where our peak is. So we could say this is unimodal, left skewed. There is a gap in our data. If I switch color, this gap here that I'm highlighting in red, which doesn't help with a red graph, is between 18 and 22. And the gap in the data may suggest two distributions, or perhaps it's a function of a low number of data values, or possibly the low values are outliers. We do not speculate when it comes to these. We just simply report that there is a gap. Okay, so we point things out and then we move on. Okay, so that takes care of shape. In terms of SOX, we go shape, center. So center, two M words that you might be familiar with. If you had to pick a single value to describe a distribution of many data values, what would we choose? Well, in previous math classes, you might have seen the two M words would be median and mean. And both are applicable, but one is more useful than the other when it comes to the data description. So most people would tell you the average value. But that begs the question, what is the average value? It is relatively simple if your data is symmetric. The center of the histogram is easily determined. But what if your data is not symmetric and it's significantly skewed either to the left or to the right? Or what happens if you have a multimodal histogram? Then what do you call the center? What do you call the average value? And is the average actually the center? So take a look at this distribution. If I said, what is the distribution of this bimodal histogram? Would we say it's here? Or would you say it's here in the middle? What is the middle in this case? What is the center? If we're looking at the median, just like the row, is the middle number. So that is one of our measures of center. The median is the value with exactly half of the data values below it and exactly half of the data values above it. In other words, the same number of observations fall below the median as above the median. The median has the same units as the data. It is the middle value once the data values have been ordered. So we need to be able to order our data in order to use medians. And that divides the histogram into two equal areas. To find the median is the n plus 1 over 2th value in the ordered distribution. So if you had 15 data points, you would have 15 plus 1 over 2. So that would be the 8th value would be your median. The value of the median is that the median is resistant to change in a few data values. So if we have skewed data, we often look at the median to describe the center. If we have symmetric data and unimodal data, we will be using that other M word, mean. So if we're looking at measures of center, we also then talk about its spread. Spread is talking about variation. So what we said in chapter 1 is variation matters. In fact, statistics is about variation. What we mean by variation is how far apart are all of the data values? Are the values of the distributions tightly clustered, or are they spread out? Are they clustered around the center, or are they all far apart? No description of a data distribution is complete without a measure of spread. Always report a measure of spread along with the matching measure of center when describing a distribution numerically. So what we mean by that is we could be looking at the range for the spread. That gives me the maximum value minus the lowest value. So we've seen this before. Range is familiar. The range of the data is the difference between the maximum and minimum values in a distribution, how far apart they are. But there's a problem with the range. So the problem with the range is that a single extreme value will have a large effect on the range of the values, and thus perhaps not a good representation of the data distribution. So maybe there's an easier way we can find a better measure of variability, how stuff vary, when using median for our center. And this comes to this somewhat new term that many of you have seen, many of you haven't seen. We call it the interquartile range. So interquartile range, or IQR, ignores data values at the extremes, so the far ends, and focuses on the middle 50% of the data. This middle 50%, or interquartile, quartile meaning quarter, and we're looking at the 2 middle quarters. So to find the IQR, we first need to know what quartiles are. A quartile divides the data distribution into 4 equal sections. 1/4 of the data lies in the first quarter. We call that Q1. 1/4 lies above the third quarter, Q3. If we subtracted the third quarter, 2, 3, 4. So we can say Q1, Q2, Q3, Q4. If we said Q1 minus Q3, and this would be 0, right? So we have 4 equal quarters. If we did Q1 minus Q3, we would have the middle 50% of the data. Obviously, Q2 is where the median lies. So to find the IQR, we do Q3 minus Q1, and that gives me the middle 50% of our data. IQR will always go with median as a measure of center. Median is the center. The spread we will use for median is IQR. Just a little bit more. The first quartile is the median of the lower 50% of the data. Or Q1 is the 25% mark. Q2 is the median of all of the data, and Q3 would be the 75% mark, or the halfway point of the upper 50%. So if we were given this data set and we were asked to find Q1, Q2, and Q3, the very first thing that we would need to do is go and put these in ascending order. So the lowest value is 5. The highest value is 56. So just to save some time, we have ordered this data to go 5, 12, 28, 30, 42. That's 1, 2, 3, 4, 5, 47, 49, 50, 52, 56. That is 10 pieces of data. To find the Q1, we first need to find the median, the middle number. So the middle number here was, if we have n is 10, n meaning the number of data values we have, if we did n plus 1 over 2, that would give me my position. So this would be 11 over 2, which would be the halfway point between the 5th and 6th number. So when you're dealing with an even number of data values, to find the median, we are looking between 42 and 47. So we just average those two middle values to get the median. So the median is 44.5. How to find Q1 is we are looking at the lower 5 values. And now we go, if there's 5 values, that would be the third value in the list. So Q1 is 1, 2, 3. 28 would be Q1. Likewise, we did this in a different color. Of the upper 5 values, the Q3 or the middle value of those 5 values is 1, 2, 50. So in our numbers, we have Q1 is 28. Q2, or the median, is 44.5. And Q3 is equal to 50. This starts giving us values that we can then calculate, because the IQR would be Q3, 50, minus Q1, 28. That gives us our spread of the 50% of the data values of our distribution. Now notice we're looking at the center cluster and we're ignoring the larger of the two values. The first and third quartiles are the 25th and 75th percentiles of our data. So what we just said, the IQR contains the middle 50% of the values of a distribution, like we shown below. If we are dealing with median, Q1, Q3, and IQR, we come up with a 5-number summary. And this 5-number summary of the distribution reports the median, the quartiles, and then the maximum and the minimum. 1, 2, 3, 4, 5. Sorry, there are 2 quartiles that we report. So the same distribution that we had before. If we were giving the 5-number summary, what we report out are the maximum, 49, Q3, which we said was 40, the median, which is 32.5, Q1, which is 20, and the minimum, which is 0. If we divide our distribution that we saw was skewed to the left and it's bimodal, we can start seeing that our minimum and our Q1, Q2, and Q3 starts giving this graphical distribution that you might have seen in middle school called a box plot or a box and whisker plot. And that's what we are creating when it comes to the 5-number summary. Again, 5-number summary gives us the median and the IQR, so this is for skewed data. What happens if we want to use the mean or the average instead of the median? So when the data is symmetric, there is an alternative and a better descriptor to the median. We can calculate the number that most people mean when they say average, or the arithmetic mean. The Greek letter sigma denotes sum. Many of you have seen this before, for calculating mean. And so what we are going to write to find the mean or the average of a data set is we are going to use the letter Y, and then this line over top we read as Y bar. To find averages, you add up the totals and divide it by the number of values you had. Mathematically, that would be sigma, or the sum, from the first term to the nth term of each of the separate Y or data values divided by the total number. So this is just a mathematical way. This is also the way the AP formula sheet would use. So you need to be familiar with what it means. It just means add up all the values and then divide by the total number. The mean, when we use that for symmetric data, is more about the balance point than it is the middle value. The mean feels like the center because it's the point where the histogram tips, hence balance point, or center of gravity. So When you are summarizing symmetric distributions, we could talk about the mid-range. So it's rarely used. I'm bringing it up, but I'm not going to make it a big deal. So we could use the mid-range. The mid-range is the easiest value to find, and its only redeeming feature is that it's quick and easy. To find the mid-range, you do the max plus the min over 2. I have seen AP-style questions that use this, which is why I'm presenting it to you. But for me, once I tell you what the mid-range is, highest value plus lowest value divided by 2, this is the last time we're going to be talking about the mid-range. For us, when we were talking about symmetric distributions, we're going to use a different measure of center, and we are going to talk about that in the last video. So before we're done with this, what do we do? Mean or median is the question for measures of center. And because the median considers only the location of values relative to the median, it is resistant to values that are extraordinarily large or small. It simply notes that they are above or below and ignores the actual size of values. So when you are dealing with skewed data, we want to use the median. So in order to make this determination, look at the data, which means draw a picture. If the histogram is sufficiently symmetric and there are no significant gaps or outliers, use the mean. Use the average. If the histogram is skewed or multimodal or has gaps or outliers, you're probably better off using the median. And again, only theory is perfect. Keep in mind, we are not looking for perfection here. Statistics is squishy. We look at approximates because real life is messy. When choosing between mean and median, look for sufficiently unimodal and symmetric when deciding to use. And I will highlight this word sufficiently. Do not be too critical of your data. If your data is significantly skewed, has significant gaps or outliers, then you're probably better off using the median. It's a judgment call, so your judgment will improve as we become more familiar with statistical methodology and what you're hoping to communicate. Just practice makes permanent. So I know I spelled that wrong. We're gonna stop here. We have one more video that's left with the chapter 3 notes. We're gonna talk about the measure of spread for using means. We're gonna wrap up with some common mistakes, and then you're off to do the homework problems for chapter 4. Also the quiz, and then this time we are adding a free response question. So see you in part 3, Falcons.